This is the video for lesson 6.5, and the learning target for this lesson is going to be I can use proportions to solve for measures in triangles. So again, we're going to continue with the idea of proportions as we did in 6.3 and 6.4, and I just want to remind you that the word proportion really means that we're looking for a scale factor. So we do have several new vocabulary, and vocabulary in geometry is extremely important, as you have realized so far. If you cannot understand the vocabulary, it's going to be a little bit, it'll hold you back some. So you're going to want to make sure that you know these theorems, okay? You don't have to know the number of the theorem, but you do need to know what they say. So the first one is the triangle proportionality theorem. If a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. So in other words, if I have this triangle here that's green, and I have arrows on the lines that show me that this line here is parallel to the side of the triangle, then that means I could set up a proportion so that it's 5 over x, because I don't know what the distance is from this for this segment right here, equals 4 over 3. So the proportions are going to be the exact same as long as we can see that there's parallel relationship between the line and that third side of the triangle. We're gonna look at an example, of course, of that particular theorem. And then the second theorem that we have is going to be the theorem 6.5, which is the reverse of what we just said. Remember, the word converse just means we're reversing it. So if a line divides the two sides of a triangle proportionally, then it is parallel to the third side. So if we do know all of these side lengths, we could find out if this particular segment here is parallel to the third side, if when we cross multiply we get the same result. So we're going to look at that one as well. Theorem 6.6 says if three parallel lines intersect two transversals. You probably remember the word transversals from way back in the first semester of our course. So if this is the case, if we have three parallel lines that intersect two transversals, then they divide the transversals proportionally. So if three parallel lines, intersect two transversals, then we're going to be using this theorem, and we're going to practice that, so you'll get to see that in action. And then theorem 6.7, if a ray bisects, cuts in half, an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional. Okay, so those lengths on the opposite side will have the same scale factor to the lengths of the other two sides. All right, so I know this is a lot of information just to hear it for the first time, but as we go through these examples, if you're getting lost somewhere, if you're not quite understanding, make sure that you write a question down on your note sheet, and then when I ask for questions in class, make sure that you're willing to raise your hand and ask that question. Otherwise, you may need to spend some extra time after school or some other time during your day, get those questions answered if you don't feel comfortable asking the questions in class. All right, so for example number 1, it says find the length of a segment. In the diagram, segment BE is parallel to segment CD, and we do see the markings on the diagram here. And it says that AB is 8, BC is 12, and ED is 9. But we need to find this missing length from A to E. Well, we were just looking at the theorem 6.4, which said if a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. And since we do see the parallel lines, this line, BE, is parallel to this segment here, DC, then we can just set this up real simply as a proportion. So the side that is x over 9, which is from this length here, equals 8 over 12. And all we have to do then is cross multiply. So we have 9 times 8 equals 12 times x, so 72 equals 12x, and if we divide by 12, we will see that x is 6. Now, to check to see that our work is correct, we could go back over here and say, what is the reduced fraction of 6/9? Because if I plug 6 in here into this spot versus the x, I'm reducing that, and I'm going to say, okay, that's 2/3. And what is the reduced fraction for 8/12? What number goes into 8 and 12? 4 does. So 8 divided by 4 is 2. 12 divided by 4 is 3. If those come out to the same scale factor, then you know that your answer of x is 6 is correct, because we're saying that side AD, this side right here, is proportional to the other side because we had this parallel line here that was parallel to the third side. So whenever you see a setup like that, just remember you're setting up a proportion. So example number 2 is going to demonstrate the opposite of that. What they're asking us to do is look at and see, is this line parallel to this segment here? So is segment PQ parallel to segment LM? How can we check? Well, we can take the side lengths that we have, or the segment lengths, and put these in a proportion, and if they reduce to the same scale factor, or if when we cross multiply they come out to the same number, then we know that's correct. All right, so let's go, I like to put the smaller numbers on top if I can, and I will. So 16 over 18 equals 24 over 27. So when we reduce, let's see, 16 over 18 is going to be reduced to 8 over 9, and 24 can be divisible, or is divisible by 3, and 27 is divisible by 3, and that equals 8 over 9 as well. Now another way to check would be to cross multiply here, so 18 times 24 should equal 16 times 27. That's a second way for you to check. And both of these multiplications come out to 432. So that means then that PQ is parallel, because we can prove that the scale factor for both of those is the same, and when we cross multiply they are the same. So PQ is parallel to LM. Alright, let's take a look at example 3, and this has to do with theorem 6.6. So let me just remind you that 6.6 says if 3 parallel lines intersect 2 transversals, then they divide the transversals proportionally. And it does say that angles 1, 2, 3, and 4 are congruent, and we have the segment lengths. So let's just identify the segment lengths here. We have 21, 28, and 32, and they're asking us to find the length of DE. So we need to find the length between these 2 points. And if those angles are congruent, then that means that this line, line L, is parallel to this line M, is parallel to this line N. And those are our 3 parallel lines. And then we would have to say that line Q is a transversal, and line P is a transversal. And so remember, transversals are lines that cut through other lines or intersect with other lines. And theorem 6.6 says that if those 2 transversals intersect 3 parallel lines, then the portions are proportional, or the segments between the parallel lines are proportional. So literally all we have to do is set up a proportion, and we don't know what this one is, so I'm going to say that this fraction, 12 over 28, is equal to this fraction, x over 32. I'm just pulling the information off of the picture to set up my proportion. Now sometimes when you see these problems, they may be in a different position, they may be turned a different direction, but all you have to do is, recognize that there are 3 parallel lines, 2 transversals, and set up that proportion. Now if I cross multiply here, I'm going to have 28 times x equals 21 times 32. So that gives me 28x here, and 672 here. Now if I divide this side by 28 and this side by 28, my value for my missing length is 24. And if you don't like to work with those huge numbers, you can always reduce this first fraction. So had I spent the time to reduce 21 over 28, I would have had a scale factor of 3/4, and then of course I would have less large numbers because I've already reduced it some. But if you're using a calculator, it really doesn't matter. I just didn't want to show you this way and have you wonder why I didn't reduce first. It's not necessary to reduce first. If you're using a calculator, you're still going to get x equals 24. So this length over here is 24. And of course you can check to see if your work is correct. If you reduce 24 over 32, you should get 3/4. Remember, this is our scale factor. So what number goes into 24 and 32? 8 does. So 24 divided by 8 is 3, and 32 divided by 8 is 4. So we know that we came up with the correct answer because we did a quick check by plugging it in. All right, we're on the back side of our paper. We're going to take a look at example 4. It's asking us to use Theorem 6.7, and I'll remind you that Theorem 6.7 says if a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. So just a reminder, this is a side of a triangle. This is a side of a triangle. And the side that is, the angle that's been bisected looks like it's angle B. And the side opposite from B is this side over here. Okay, so it's saying that the portions of AC that we have in the diagram, where this point is right here, where that ray, that angle bisector hits there, it creates equal proportions. So the challenging part here is that we don't know what the length of DC is. We don't know what the length is from just here to here. But we do know that the entire length of that side is 33. It tells us that right here. So for this segment, we're going to have to say that that is 33 minus x. X is the length from A to D. So DC is 33 minus x, and we're going to use that to set up a proportion in just a moment. So anytime you see a bisected angle like this, you can know that the side opposite is proportional to the side lengths of the other two sides. So watch carefully as I set this up. We're going to have 45 over x. Notice that those are the things that are super close to each other. This 45 and this x go in a fraction. And then I'm going to say that's equal to 54 over our 33 minus x. Okay, so the information that's on the right side goes in a fraction, and the information that's on the left side. So this is the left side, this is the right side. And of course, in some other diagrams, it'll be twisted around or flipped a different direction, but you just have to notice if the angle is bisected, this is the type of problem you want to set up. So what I'm going to do is I'm going to cross multiply. And when I cross multiply here, I have to remember to distribute that 45 to both. So let's go ahead and do that. So 54x equals 45 times 33 minus x. This does take a little bit more time because we have that x there and we have to actually solve for it. But if I go ahead and multiply my 45 times 33, I get 1485 minus 45x. And to get rid of that negative 45x, I'm going to add 45x here and 45x here. This is going to cancel, and I'm going to end up with 99x equals 1485. Divide by 99. So a lot of this is algebra. Once you get the problem set up, you just have to use your good algebra skills and make sure that you're careful with your calculation. X is going to be 15. So to check and see if my answer is correct, what I can do is I can plug 15 in here because that's what x is, And then I can also say, well, if x is 15, then this length right here is going to be 18. And I'm going to set up a new proportion to check to see that my work is correct. So 45 over 15 equals 54 over 18. Okay, and do those reduce to the same number on both sides? Or if you wanted to, you could check to see that this cross multiplication and this cross multiplication ends up being the same. But 45 divided by 15 is 3, and 54 divided by 18 is 3. So we know then that our answer of x equals 15 is correct. So again, if this is confusing, or if you think that you need to rewatch this video, this portion of the video, please do that. But like I said, anytime you see that there's a bisected angle, an angle bisector, then this line becomes a place where you can say, oh, now I can set up my proportion and just solve. A lot of them will not have something that looks like this. This was a pretty challenging one, but I think if you look at other problems, you're not going to see that type of difficulty. Now, for the next set of problems here, you're going to practice these on your own, and it's asking you to practice each kind of problem that I've already presented. So you're going to want to go back to your example number 1 when you're looking at this problem. Example number 1 is just like that one. This one is like example number 2. This one is just like example number 3. And then, of course, number 4 is like example number 4. I am going to give you a little answer bank. So the 3 problems do need an actual answer. And so I'm going to tell you that your answers are, okay, so these are the 3 answers that you should be looking for. Not in that order, but those are the 3 answers. For this one, number 2, it's just asking you to make a determination of whether MO is parallel to LP. Is this segment parallel to LP? So make sure you show work on, and if you end up having questions, please make sure you ask about these problems. Thanks for watching.